Okay, so guys, today we have Yikun Jiang from Cornell University talking about focusing bounds for CFT correlators and the S-matrix. We thank you, Yikun, for accepting our invitation, and please take it away.
Yeah, thank you. Thanks for the invitation for me to give a talk here. So today I will be talking about this paper on arXiv together with my advisor, Tom Hartman, and two postdocs, Francesco and Amir. The title we gave for this paper is Focusing Bounds for CFT Correlators and the S-matrix. So before talking about focusing, I want to begin by motivating something related to energy conditions. So first of all, energy conditions are super important in general relativity. They are the most important ingredient, I would say, in, for example, the proof of the area theorem, the proof of the singularity theorem, the proof that there is no traversable wormholes, or these days, people use the fact that you can violate the energy, some energy condition to actually create a traversable wormhole, which is a very hot topic. And in the context of ADS-CFT, where a theory, gravitational theory in ADS is equivalent to CFT on the boundary, the average null energy condition on the boundary, which we call boundary ANEC, it's related to causality in the bulk. The way to see it, I will present a very simple argument. I can make it very precise, but I just want to be quick. So just consider a small perturbation around ADS. So I have my ADS metric in Poincare coordinates and plus some perturbation. When this is the case, you can see that if you shoot in a light ray in the U direction, there will be some time delay. Time delay means that there will be a time difference with respect to the empty ADS. And in this case, it's very easy to see if you look at the null geodesic equation, you integrate it, you will see that the change in the V coordinate is given by this equation. I'll explain more if you think it's confusing. Forgive me for a moment. So the point is that causality really tells you that this quantity must be positive. You cannot go negative in gravity because this is the time difference. If you create some perturbation in the bulk through some operation on boundary, then the perturbation must be such that the perturbation you create will give you some positive time delay. You cannot really create something that gives you a negative time delay. So this is the statement of causality. And now in ADS-CFT, if I look close to the boundary, if you are familiar with ADS-CFT, you know that the boundary stress tensor will be dual to the CFT. Sorry, the boundary metric tensor will be dual to the CFT stress tensor. So especially when you are close to the boundary, these two are proportional to each other. So the fact that you must obey causality in gravity, which is this quantity must be positive, when you are close to the boundary, can be translated into the statement that this quantity must be positive in CFT. So you see how they're related. This is a quick holographic argument. And actually, I want to make a quick comment, which is for any CFT, not even holographic CFT, you can study ANEC in flat spacetime. You can prove it directly without using holography, using bootstrap or quantum information techniques. We can comment on that later. It's not the main focus of this talk. But we want to ask another question, which is we have the average null energy condition on the boundary. It's great, but we can ask another question. There is actually another ANEC in this story, which is the ANEC in the bulk. And what this means, and is it true? And if it's true, what does it mean for the boundary CFT? That's a question we want to ask. So let me, because this point is kind of confusing, so let me stress this again. There are two types of ANECs. In ADS-CFT, where this is the bulk, this is the boundary, there is one that lives on the boundary, which is the one that's mostly studied by people. That's called a boundary ANEC. That one tells you that the CFT stress tensor integrated on null ray must be non-negative. And that's related to what I just explained to you. That's related to the causality in the bulk. It tells you that when you create some perturbation, the time delay must be positive. On the other hand, in this talk, I will be start talking about this energy condition, which is the energy condition in the bulk. And this is the one that will be related to focusing. And especially we want to explore if this is true, and if it's true, what it implies for the boundary. And this is a problem that has never been studied, and I hope I can convince you that it's related to focusing, and it's an interesting question. Okay, so let me really pose the questions. The question is the following. First of all, what does this boundary in ADS mean for its the dual CFT in ADS CFT correspondence? Secondly, if this condition is true, then it's very natural to ask, not only for theories with gravity, you can ask if I add higher spin particles, especially in string theory, is this condition true, or should I replace it by something else? And those are the two questions we'll have in mind. And I want to, after today's talk, I hope I can convince you that there is such a thing, and we call it the focusing bound. These notations, just forgive me for a moment, I put them here just to show you the results. So the notation is not clear, but that's fine. I'll explain it. So I want to tell you that what we found is that these bounds actually in CFT tell you something about correlation functions. Or when you take the flat space limit, you will get some constraint on S-matrix that takes the following form: two inequalities that hasn't been studied before, and we check that they're true. I will show you why it's true, and also they're true in string theory, and that's the idea here. Okay, so let me first tell you the outline of the talk. First, I will show you what is focusing in asymptotically flat space-time, how is it related to the energy condition I just mentioned, and then I will translate it to some constraints on S-matrix. I will start from flat space-time because it's much easier to present. The operators are simple, the pictures are simple. So in this case, I hope it can give you some flavor of what's going on. And the main goal is to study ADS CFT, but you can think of this either as an independent statement, or you can think of it as coming from the flat space limit of some ADS CFT, coming from some ADS CFT limits. And next, I want to show you that this part is really about ADS CFT. First of all, I want to show you that there is such a positive operator in ADS, and you can translate that into CFT language from something called Regge OPE. Yeah, especially I think at Portal, people might get excited. I'm excited at least to talk about Regge limit here, and we'll see how actually why that's true and how it's true. And next, because this is an operator statement, next I will put it into correlation functions. And so I will just show you how that positive operator tells you some constraints on CFT correlators. And the first 4 bullet points here are all for theories with gravity. So you should imagine the particle is highest spin, is spin 2. You can have gravity. You can have gravity with higher derivative couplings, but there are no higher spin particles. Finally, I want to mention to you how to generalize these things into theories with higher spin particles in conformal Regge theory, including string theory. Okay, so this is the goal. Yeah, just let me just stop here for a moment. Any questions so far?
No, I think you can proceed.
Okay, great. So let's look at the first thing, which is focusing, which I'm not sure if people are familiar. So let me, I think it's I tried to make it pedagogical, but please stop me if anything is not clear. So the idea is first of all, I want to show you the connection to average non-energy condition. So the idea is as follows. I still consider a small perturbation, in this case, around flat background. So it's asymptotically flat. There's no that 1 over z squared there. This is just flat metric. I have some perturbation. There's some higher order terms. Now, let's imagine I have a high energy proparticle. It travels initially in the u direction. The idea is that if I look at the geodesic equation, I can see that if I until I reach the u equals to positive infinity, the v direction will get shifted. And here I'm illustrating a very special example, which is they shift at just u equal to 0, a very special point. In general, you can just imagine it's changing gradually. This geometry will be useful later because it's related to the so-called shock wave. But just keep this in mind. Like this is a simple picture, a very simple example. Just in gravity, the slogan is that gravity always slows you down. So perturbation will only give you something that create a time delay. And causality is a statement that this guy must be positive, just pretty similar to the one I gave you in the introduction. Now the idea is as follows. This is an integral for the metric tensor. But to get the stress tensor, it's actually very simple. You just need to hit this guy with some Einstein equation. In this case, it's very simple. For this metric to linear order, the Einstein equation is just the transverse Laplacian acting on this quantity. And if you bypass this integral, you see d square will hit on h and make it into the stress tensor. So if I hit this guy by d square, I will get this equation, the equation by the Einstein equation. And this is what we want. Okay, this is the averaged null energy. So ANEC is equivalent to the statement that the left-hand side, which is the transverse Laplacian acting on the time delay, is negative or non-positive. So you can see the difference. I want to stress again here. This is the metric tensor. This is the integral of the metric tensor. This is related to causality, and Einstein equation, especially the energy condition, is related to this derivative, and this is related to the ANEC. These two are different. However, this guy is stronger than the first one because you can see if this ANEC is true, then actually I can get the condition that this one without the derivative is true, because when I have this equation, I can solve it using the Green's function. And the Green's function is simply negative. So if I know ANEC is true, I can get the condition that causality is true. So this is a condition stronger than causality. This is basic. What I present to you is just the quick version of what Gao and Wald proved as the causality condition. But you can see there is a stronger condition, and indeed ANEC is such stronger condition. Okay, so this is the part about energy condition. Now I want to really talk about focusing. So here things looks a little bit tangential, but you immediately see that they are actually related. So instead of considering a single particle, only a single word line, now I consider a family of null geodesics. Like everywhere there's geodesic. Initially they are parallel, all in the u direction. And there's a name in GR. These kind of things, non-crossing geodesics is called a null congruence. And later I will use these words interchangeably. So a way to study these type of congruence is by some geometrical quantity. First of all, I will define something called expansion, which is defined by the trace of the derivative acting on the normal direction. And there you can do some GR analysis. It's a kinematical fact that you can rewrite this in terms of the transverse area of these null. Like you can study the transverse area separated by these null rays. So you can show these two are equal. Essentially, this quantity, after you rewrite it, will be the derivative of the changing rate of change in the transverse area. So this quantity, first of all, you see initially they are parallel, so there is no change. So initially the theta will be 0 because they are initially parallel. And if I can show what does focusing mean, focusing simply means the area is decreasing. So this quantity is very highly related to focusing. If I can show it's negative somewhere, then it means it focuses. And in this case, actually, you can show that it's immediately related to the energy condition, and it is what we want to show. Okay, so let me first tell you one more thing, which is more general than the thing I will present to you, which is actually just the previous equation. You can rewrite it. It's purely kinematical. Just rewrite the derivative, separate them into different pieces. There are the trace piece, there are the trace free piece. and there is another piece related to this curvature. So it's not important if you don't know what shear tensor is, but just notice that there is an equation. I think for GR people, this means focusing. Because what I want to show is theta has some, for example, is negative. But you see, these are the first two terms are square of something with a negative sign. So they must be negative. If I can show that the last term is also negative, then the right-hand side will be negative. It will tell you the change in rate is negative. Okay. And that's basically most of those theorems start from here and do some analysis. So basically assuming this is negative. And by the Einstein equation, R mu nu is related to T mu nu. So you see it's related to energy conditions. That's the idea. But it's not important. You don't need to know where this comes from, because in my talk, I will be focusing on linearized gravity. And at that level, the first two terms are quadratic in metric. So you can just ignore them. So at linearized level, the change in the expansion is related to the curvature on the right-hand side. By the way, there's one more thing I want to say. This equation is called Regge equation. And if I get this equation, now I can integrate it. So I know this lambda is the affine parameter. If I integrate it, I will get the theta at infinity, which is the final position for lambda. And initially, I told you they're parallel. It's 0. So left-hand side will tell you the theta when you go to infinity. On the right-hand side, a little bit analysis in the geometry, you can just show that you can calculate the curvature in this case, I showed you, and it's given by this quantity. So this equation is telling you that at the final stage, this theta will be half of the quantity I just described to you related to the energy condition. It's not surprising, because if I really use Einstein equation, this will become the energy condition, right? So, but at this stage, everything is purely kinematical. I haven't used Einstein equation yet, but you can immediately see, I just told you, if theta is negative, it means the transverse area is decreasing. That is another way of saying light rays focuses. So focusing is the statement. In this very special case, you can see immediately this quantity I derived, I told you, related to the energy condition, is related to focusing, and I want to show it's negative. So that's the idea. Okay. Yeah, let me pause a moment. I know it might be confusing if I haven't seen this before when you learn GR. So any questions so far?
No, I think you're doing a great job in explaining it.
Okay, great. Thank you. So now let's really try to translate this into S-matrix, because that's what we really care, right? Delta V is it's still talking about some particle, word line, geodesic, but actually it's very simple to translate this into constraints in S-matrix. So the idea is as follows. Now, instead of considering a general perturbation, let's consider a perturbation created by a highly energetic particle. Another name for it is called a shock wave. So the idea is, imagine now, not only you have a particle moving in the U direction, you also have a highly energetic particle moving in the V direction. So if it's really highly energetical, it will be localized on null ray in V direction. And the solution of this type of the back reaction of this highly energetic particle can be solved. And the solution is called shockwave geometry. And what it does is, if you have a probe particle, which is the U direction particle, traveling in this direction, when it hit the shockwave, it immediately gets time shifted. And yeah, so that's the thing we will study here, which is a special example, but in most cases that's already enough. And the idea is as follows. To describe such a geometry, there is one thing related to it, which is, now let's study scattering amplitude. And I can study the 2-to-2 scattering amplitude by scattering of these two types of particles. The scattering amplitude will be called, as usual, as M. S and T are the Mandelstein variables. S is related to the center of mass energy. T is related to the transverse exchange momentum. And there is something called impact parameter space representation, which is essentially just a Fourier transform of this quantity, where you trace the transverse momentum to the impact parameter, which tells you in transverse space, I suppress the direction here because it's kind of hard to draw. Just imagine in transverse direction, they are separated by x. So the left-hand side will tell you, you describe some scattering amplitude by the energy and how far these two particles scatter. Now, the idea is that in the Yikun regime, which is high energy regime, which I suppressed some conditions on, for example, you cannot create a black hole. I will suppress that, but roughly speaking, it's the high energy regime where the energy is so high, at least much larger than the inverse of the impact parameter. Then you can define something called phase shift. And the magical property is that Yikun regime, I think amplitude in impact parameter space will exponentiate. So the phase shift will be related to the tree level impact parameter space amplitude. Yeah, so just for example, I show you a simple example. Suppose I really consider an experiment by a scalar particle with a graviton. Then just consider this amplitude and do the Fourier transform. You will get this tree level impact parameter space amplitude. And the claim is that this is equal to the phase shift that you would define usually if you're familiar with scattering amplitudes. But anyway, okay, so that's the result. And there's the next thing I want to tell you is actually can show, I will skip it, you can ask me for roughly how it works. We can show that in this setup, actually the time delay is related to this phase shift by this very simple relation, which is now S is the center of mass energy square. So it's related to the product of the energy of the probe and target. So now if you take derivative with respect to the probe energy, then you get the time delay. Okay. Yeah, I can give you a quick reason for it. It's because the phase shift is really a phase. And it tells you after the scattering how, just imagine these particles are wave packets. So this phase shift is really telling how the phase changes. So by studying the phase, how it depends on energy, it tells you how time changes. That's the rough idea. But anyhow, so you can see we know that we want to study this delta V. Now we translate this using this shockwave setup into a condition onto this phase shift. So the causality, especially delta V greater or equal to 0, is translated to the condition that the derivative acting on S, I just change variables here because here it's used as S, act on this delta must be greater or equal to 0. So that's causality. And what is focusing? Focusing is the statement that the transverse Laplacian acting on it, excuse me, is negative. So just act it on derivative, you get negative. So that's focusing. Okay. Those are the conditions in real life how we want to study like what those conditions are for observables. So actually the first thing is not new. There is a famous paper which I will denote by camps because these four authors study this problem. They really study causality constraint, which is the first one. If you do it, for example, I show you a very simple example, which I think is the most illustrating one. You can study if series with Gauss-Bonnet couplings are allowed. So here, the Gauss-Bonnet coupling will change this vertex. So by studying this diagram, the lambda will enter through this 3-point function here. So now you can calculate the amplitude, do the Fourier transform, you get a phase shift. You can study whether the first condition is satisfied or not. And what they found is that as long as this lambda is not 0, this amplitude depends on the polarization of external particles. I can always choose some polarizations and some impact parameters to make this quantity actually have the wrong sign. So if you can find one with a positive sign, then I can show you that there is a way to create a negative sign one. In other words, whichever sign, like as long as this is non-zero, this condition will be violated in some cases. So it tells you that actually the lambda must be 0. Or to be more accurate, because we must, these conditions, you are studying effective field theory, so you must still land in the effective field theory regime, especially the delta V cannot be smaller than the resolution, which is set by the cutoff. So actually lambda must be smaller than inverse cutoff. So that's the idea. It's actually very interesting because simply using causality, you can rule out this theory. This theory is not allowed. It doesn't have a ghost. Everything seems to be fine, but magically by causality argument, you can rule it out. And I want to show you actually, not only using the causality constraint here, you can actually use the focusing condition to get exactly the same answers. Actually, you can reproduce the whole paper by using the focusing constraint for a very simple reason, actually. Because you see, I said that if you act this by d squared, you will get the average non-energy condition. So if I solve it using Green's function and take this form, especially the subtle thing here is that these two are not equivalent. One is stronger than the other because of this integral. Only right-hand side has a sign implies the left-hand side, not the other way around. TU, one more thing to tell you is TU total means the matter energy plus the pseudo tensor contribution here, because here you should really imagine you put everything act like the left hand side is related to the transverse square acting on the metric tensor. So everything appears in Einstein equation on the right hand side, including the pseudo tensor coming from the graviton energy is included on the right hand side. So previously I said this is stronger. This is why the right hand side condition is stronger than causality, but because it's a shockwave, they are localized in transverse directions. So actually there's a delta function here. So you actually do the integral. So the Green's function will come out. There's no left integral in transverse direction. That's why actually in this case, you can see the integral of the, if the right hand side has a sign, left hand side must also have a sign, and vice versa actually, because this is simply a negative function with the negative sign is positive. So they have the same sign at the same time. So actually in this case, the conditions are equal. Focusing is equivalent to causality. And another way of saying is it's equivalent to the, this is called generalized ANEC because you include the graviton energy. So yeah, that's the idea. Actually, these are equivalent here. So whatever you can get in that paper, you can reproduce it using the focusing inequality. And in our paper, we studied a very specific example of this. Okay. Oh, there's one more thing I want to tell you. You can generalize this analysis to theories that involve higher spin particles. Previously, I used some Einstein equation geometric arguments, but as long as you include those particles, those analyses don't apply. But still, in that case, so we have no reason to expect to like the focusing condition like this to be true. It's actually a very interesting observation that you know the amplitude explicitly. So just calculate, and you can see if you have isolated massive higher spin particle, it will violate our bound. On the other hand, in string theory, the Virasoro-Shapiro amplitude actually satisfies this bound for a very magical reason. As I will talk about the CFT version of it, and you can think of this as coming from the flat space limit of that story. So I will just postpone the discussion later. So okay, that's everything I want to talk about for the flat space case. Any questions so far? And just pause for a moment. Okay. So now,
what is the case that it violates?
Oh, if you have just consider the amplitude, suppose you the 2-to-2 scattering, you have a scalar and massive higher spin particle and mediated by some graviton exchange. You can calculate the amplitude and do the Fourier transform, it violates that. So isolated higher spin particles, they are inconsistent for other reasons, but for our bound seems to suggest that they are also not allowed.
Okay.
Yeah.
Thanks.
Yeah, no problem. Okay, now let's really come to CFT. I hope you get a flavor of what it means in flat space, but ultimately ADS CFT is more interesting. So let's just study the ADS CFT version of the story. So first of all, there's a very natural question. Is ANEC actually true in ADS? And I can tell you it's actually true for a very simple reason. It's because at leading order, all the contributions are coming from the perturbation for the state. So you just, in order to see that the expectation value of the energy is positive, you just need to show that this operator itself is a positive operator in the leading order expansion. And especially this is doable because essentially fields at leading order in ADS are just free fields, and the dual of them are called generalized free fields. So you can actually show that using creation and annihilation operators very explicitly it's a positive operator. So roughly it goes as follows. The energy, you can write it in terms of normal ordering like this. Phi's are bulk fields. Now there is a formalism called HKLL. You can express these bulk fields in terms of boundary operators using K as a kernel. So that's the equation. And then these O's on the boundary are generalized free fields. So they are essentially just free fields, but to give the correct 2-point functions, you have to insert this extra p to the power of delta minus d here. Okay, now you have all the ingredients. The kernel is known and the expansion is known. Just plug it in. After you perform all the integrals, you can see that this is positive. It's a positive operator. For actually not, if you have done similar calculations, it might seem obvious to you, but actually one thing I want to mention is this operator itself, if you don't integrate on this null line, is not positive definite because of normal either. You might think, oh, it's a square, so it's a positive, but it's not true because there is normal ordering here. So some of the orders will get changed. So it's not a square of something. But those worrisome terms will be 0 after smeared in this null direction. So great. This is a positive operator. You can just show this explicitly. It's positive. So any expectation value must be positive. So in ADS, you know why that's true, but what we care is actually what it tells us about CFT. Can we learn something? Actually, indeed, that's what I'm going to tell you. So first of all, let's study follow the exact same logic as the flat space case. So what does focusing mean? What is related? How is it related to energy condition? First of all, we write on the time delay for this perturbed metric. It almost look the same, just there is some extra factors here. And the idea is for this to be related to the energy, I still use the Einstein equation. But in this case, because this is ADS, the equation will be related to the transverse Laplacian instead of the Laplacian in flat space. So it's a Laplacian in hyperbolic space. If you do this, then you see right-hand side will become the average non-energy condition in the bulk. The interesting thing, so now I know right-hand side is positive. So the goal is now, how do I translate the left-hand side? If I can translate left-hand side, both quantities, one thing related to this this time delay, one thing related to this differential operator into CFT language, then I will get some constraint in CFT. And that's exactly what I'm going to do now. So the idea is as follows. First of all, let's look at how to get this time delay. So I want to show you, actually, they are gotten from the Regge OPE. Yeah, people here are familiar, but I still want to explain it. So the Regge OPE is as follows. So the Regge OPE means now you consider two operators in the CFT. You boost them together. The boost means you also, like when you do the boost, you also need to keep these the product fixed, and that's called Regge limit for the kinematics. There's one thing I want to mention, which is in bootstrap literature, people also study something called Yikun limit. These two are actually different. The difference is I show in this diagram. In Regge limit, you do the boost directly. In Yikun limit, you first approach the Yikun, then you take v to infinity. So what's kept fixed is different. And the right-hand side is also related to ANEC, but that's related to the ANEC in flat space-time. It's not the bulk ANEC we are going to study here. So if you don't know what I'm talking about, just ignore it. What really matters here is the Regge limit. Okay, now actually in Regge limit, something nice happens, which is the dominant contribution in the OPE will come from the largest spin operators. Here, everything I'm talking about will be related to gravity. There's no higher spin particles, so the largest spin particle is the graviton. Now, yeah, I will present to you the simple version, which is these two operators are extremely heavy because in this case, it's simple. You can use the geodesic approximation, but I can show you the answer. You can actually do it even for non-heavy operators. The answer is just this guy smeared in some transverse direction, but you can get the OPE basically just from studying a Yikun diagram or geodesic approximation. So you can show that yeah, the reason is because you see, if you study graviton exchange when it's heavy, actually the expectation value will be related to the length connecting these 2 points. So, and indeed that's related to this integral of HUU. So in other words, if these operators are heavy, if they are in Regge limit, then the Regge OPE of these two operators coming from the graviton exchange will be written like this. And that's great. First, let me explain 2 things. First of all, this integral now is in the bulk. It's somewhere here. I draw here. It's a geodesic that connects 2 points on the boundary, and because they are sent to infinity, actually, the geodesic is almost just a light ray parallel to the boundary, and as a constant. Oh, sorry, it's not Zeno, it's Ada. Furthermore, it's actually great. This guy is related to the time delay, right? And so that's why I say it's the bulk light ray operator that's related to causality. Okay, first we achieved our goal. We get the right-hand side, which is something in the bulk in terms of OPE purely on the boundary. There's one more thing I want to comment is this is the OPE in terms of bulk light ray operators, but you can still ask if purely in terms of CFT language what it means. So just notice that this bulk metric tensor, you can reconstruct it using maybe the HKLL formalism. It's equal to, in CFT language, the stress tensor and some multi-trace operators formed by these psi operators. So in the bulk, it's just single field, but on boundary, you have a lot of fields. And actually, these multi-traces, usually people take limits, smear them, ignore them, but here you will see it plays a very important role. Those are the ones that give you the energy, actually. Okay, I'll just explain now. But the idea is as follows. Now, okay, first of all, we have achieved getting this integral of HUU. Now, if I can find something that's natural purely in CFT, that can reproduce this vector, then I'm done. Okay, everything will be in CFT. So how to get it? Actually, simply you notice that, well, this is the Einstein equation, is the equation of motion for the graviton, which is the particle exchanged. So how to get that in terms of boundary variables? The idea is as follows. So essentially, to get the OPE, I can study a Yikun diagram like this. And there is a very natural way to get the equation of motion for the exchange particle, which is using this following argument. So this is a Yikun diagram. It has ADS isometry, which means the generators on the boundary for these 2 points plus the bulk generator must annihilate this diagram. And now you notice that if I take the square of this bulk generator, then I will get the Laplacian. Laplacian is what's giving you the equation of motion for this bulk field. And it's great because on the left-hand side, you also get something you're familiar, which is, in this case, if you move this to the other side, take the square, right-hand side become the equation of motion, left-hand side is just a conformal Casimir operator. So in other words, if I add the conformal Casimir on my OPE, I will get the bulk equation of motion. Okay, that's the answer. So I can give you some more explanation on that related to CFT. This I think is very important and never explored before. So let me summarize in this diagram. Hopefully it will make sense. So I've already told you that this is how the field in terms of bulk and boundary observables in terms of OP look like. And this guy is the HUU. Now I act this operator Casimir, subtracting the eigenvalue for the graviton on the two sides. So the left-hand side by the Einstein equation will become this bulk energy. And the right-hand side, you see, because this is a stress tensor, it will be annihilated by this Casimir operator, because this is simply an the stress tensor is an eigen operator. I'm using the eigen value 2D for the stress tensor here. So I'm only left with the double traces. So this gives you something very nice, actually. It tells you that because this cancels, this get killed. So the double trace operators, when you act it on the by the Casimir, will give you the bulk energy. So the multi-trace operators actually get all organized into the bulk average null energy by acting the Casimir. Okay, so let me just summarize this using an equation. I think this is one of the most important formula. So the idea is that right-hand side is something related to an operator in a bulk. And on the boundary, the way to extract it is by looking at the Regge OPE of any CFT operators. You need to subtract the identity. You act the Casimir. Here I'm writing the version for like very heavy operators. I can show people if people are interested. It's just get messy if operators are not light, but there's a similar equation there. Okay, so first of all, let's see how it relates to the previous discussion relating the bulk and boundary. It's really important to distinguish the two because sometimes people get confused. Just to notice one thing, which is the CFT ANEC is related to this metric tensor. So let me just solve this equation by using the Green's function. And when you do that, you take this equation close to the boundary, then you will see that effect that I just told you, which is the CFT ANEC is related to the bulk ANEC smeared over some kernel. There are some constants here which I ignore if they are not super important. Just notice that this tells you that actually the boundary Lightweight operator, you can actually get them from the bulk Lightweight operator by some kernel. And this is also for the same reason as I explained before, right-hand side would be stronger than left-hand side. So the slogan here is the bulk ANEC is stronger than the boundary ANEC. And you can see it here, this equation. Yeah, let me pause for a moment because this part is kind of confusing. Any questions? Okay, so now let's really see what this constraint means in terms of correlation functions. Okay, OP is great, you have operators, but what we ultimately do will be studying correlators. So the idea is also simple. We have extracted this OPE, and it's a positive operator. So expectation value of this operator in any states must be positive. Now, the idea is that if now I choose my kinematics in my correlator such that the kinematics is reflection positive, then you can always slice open this Paschen integral by viewing it as an overlap. So, for example, I will mainly focus on these 4-point functions. Just think this O as some operator inserted in some Euclidean time, and the left-hand side O will be the Hermitian conjugate time of it. So these two will be reflection positive, and this Euclidean operator insertion will create a state. So you can really put a cat here and a bra here, and it will be an expectation value. Because we just said that this psi OP is positive, it tells you that this 4-point function must be positive because this can be reinterpreted as an expectation value. Okay, so what does it mean in terms of cross ratios? So the 4-point function cross ratio is defined here. For convenience, I will introduce these parameters. Actually, not only for convenience, because these guys have physical meanings. So first of all, what is Regge limit? Regge limit is sigma go to 0, eta fixed, and you must go to the second sheet. I think people will know what second sheet means. I'll have some more to say about it, but forgive me for a moment. Just like skip this point if it's not clear. The eta here has a physical meaning. I already used it, but let me stress this again. It tells you how deep you can go into the bulk. So in Regge limit, you can tune this eta, right? Only sigma is sent to 0, but you can tune different eta. Actually, you can detect very deep into the bulk by tuning this eta. That's the idea. So that's why we introduced it in the first place. In this reflection, positive kinematics, eta is real and sigma is purely imaginary. Yeah, and it must be actually imaginary, positively imaginary. Okay, if I study this kinematics, the previous statement for the operator will get translated into this constraint on core 4-point functions. So I still need to subtract the identity, but it can be done by considering the discontinuity of this correlator. So if you consider the discontinuity, you acted by the Casimir operator, you will get a positive. You will get something positive. It now is a positive number, and the Casimir you can use conformal invariance. You basically is done by Dolan Osborne. I forgot to put the reference here. You can rewrite that as a differential operator. In Regge limit, look like this. So it's very straightforward. So what to do? To check the focusing bound, what it need to do is just to give me the 4-point function. You take the disk. You go to the second sheet. You take disk, then act by this differential operator. Then check whether it's positive or not. Okay, very simple. And indeed it is. I just show you the simplest example, which is 4-point function for a series minimally coupled to gravity. The amplitude is given by the Witten diagram. The Witten diagram is known. There's no closed form expression, but anyway, you can do this. This is for dimension equal to 4 for some technical reasons, because the functions are nice. Otherwise, you'll see hypergeometric ones. But when you do that, you see immediately this is positive. Okay. Sigma here is purely imaginary. Positive, it will cancel this I. Everything else here is positive, so it's just positive. And the nice thing, actually, of course it should be, because we show that ADS is a positive operator. But nice thing here is it's simple. It's a 4-point function, but you can study 6-point function, 8-point function, 10-point functions. They must all have a definite sign. Okay,
can I ask a question? Is it super clear that the discontinuity will always give you a positive number? Because this follows from the equation that you wrote.
Yeah.
Right? You have the point function properly normalized, and then you act with some discontinuity, and this will be discontinuity of an integral over the stress tensor.
Yes.
Positive, but it's always clear that it has to be positive.
Oh, you mean the discontinuity itself, right?
Yeah, that is.
Yeah. I was just explaining. A very good question, actually. Yeah, you can see it from bootstrap argument, actually.
Okay.
That's something I will tell you, actually. Okay. So just to see that gravity is not so interesting, like you know everything, you know what's going on. Let's just go to conformal Regge series. Will be very clear, actually, why that's true and how that's true. So I've told you everything about gravity. Now let's really go to the regime, the stringy regime, where you have higher spin particles. In terms of conformal Regge theory, string theory is just a special example. So the idea is as follows. First of all, it's done by the Portal people, actually, very nicely at very early time. In Regge limit, the correlators, specifically this 4-point function, you will go to the second sheet. So there are some. So what does Regge limit mean? Initially, in Euclidean signature, operators are up and down. They are symmetric across this, like related to this y equal to 0 axis, the x-axis. And to go to Regge limit, you have to analytically continue. You have to wind this cross ratio z to go across the branch cut starting from 1. So when you do that, people call it the second sheet. And when you do that, actually something very interesting will happen, which is you can decompose the 4-point function into conformal blocks, and each conformal block by block, when you do the continuation, behave like this. And you can immediately see, because we're sending sigma to 0, this guy is divergent, especially it's more and more divergent for larger and larger J. So I cannot just continue term by term, then add them together because it's very divergent. What the idea is, we have to first resum over the spin, then do the continuation. And that's dubbed as conformal Regge theory. I'll skip the details, but the result is look as follows. The discontinuity is equal to this integral. Notice one thing important is physical operators. Previously, if you do it term by term, it's on the imaginary axis of nu. I've already rotated it into the real axis. And once you do that, this is the equation. Omega is a function, known function called harmonic function. It's not important. It's the function form. Functional form is known. The important thing are several. First of all, this alpha mu encodes the OPE coefficients. It has poles coming from double traces, single traces. It's not that important. The more important thing is what's here called the Regge intercept. The Regge trajectory. And for example, I will show you the case for string theory, which is dual to n equals to 4 super theory. This Regge trajectory looks like this. When I'm at infinite coupling, the trajectory is flat because I only have the graviton. That's the case we study for gravity. Now, when I move away from this infinite coupling limit, you gradually see that this curve always takes this shape, which is a curve like this. It's convex. So this shape actually will be important when you evaluate this integral. And yeah, just there this diagram. And the lesson here actually is for n equals to 4 is known for large n theories. And actually it's believed, although not proven, I think it's believed that for any large n theories, the leading trajectory look like this. I would take it for granted. But if you're more conservative, just take what I would say as follows, only as working only for n equals to 4 theory. So the idea is now as follows. Now, this is the discontinuity. I can also check. I know the functional form of this, the Casimir. You act on it. You see a magical thing, which is, okay, it's probably not that surprising. This function itself is actually an eigenfunction of the Casimir. So when you subtract the eigenvalue for the stress tensor, it will be the difference between the eigenvalue for this operator corresponding to nu and the stress tensor. Okay, so in argument, you only get this extra factor. The idea is that in Regge limit, which is sigma go to 0, eta fixed, this integral is dominated by a saddle point at u equals 0. The reason is as follows. I'm integrating on a real new line. So you should imagine it's going like into the page. If this function is an analytic function, if on the real axis, if on the imaginary axis, it could take this shape, then on the real axis, which is into the page, it must look like a saddle point. Okay, it must take this shape. So that's the idea. So you can always evaluate this by saddle point approximation. And once you do that, this factor will come out. It's just an overall factor. You just replace this by a value as 0. And one more comment is this J of 0 is called Regge intercept because yeah, the Regge intercept plays a very important role when people initially study string theory, Regge theory, but it is just what it is. It tells you the intersection at this nu equal to 0 point, which is here. Okay. And you see it's always smaller than 2. Actually, there's a reason. So I'm about to tell you why this must be negative and if this guy has a definite sign. The idea is as follows. The Regge limit is studied also somewhere else, which is when people study quantum chaos. So the way to see it, I like to see it, is usually quantum chaos is expressed as a thermal correlator look like this. But the idea is that flat space CFT is related to thermal physics because it's related to thermal physics in Rindler space. So if I introduce this Rindler coordinate, where Regge limit will be translated into the fact that t goes to infinity, x is fixed. So the correlator will look like this: 1 plus 1 over n squared, e to some very large t goes to infinity times a coefficient. Okay, now I will tell you why it has a definite sign, because here it's just the disk. The disk must have a sign because we're detecting quantum chaos now. And there are bounds proven by considering quantum chaos by these the so-called MSS bound. It tells you two things. First of all, this disk must be negative. So this term must be negative so that you have quantum chaos spread. Okay. The second thing is that if you're familiar with the chaos literature, this coefficient here is the so-called Lyapunov exponent. And it must be smaller or equal to 2. We actually see it here. It must be smaller or equal to 2. But this is by direct calculation, but there's a reason for that. It's because of the chaos bound must be smaller or equal to 2. So by using these two facts, you see the two terms here, disk here is negative, and the prefactor here is also negative by the other chaos bound. So the two chaos bound combined together will tell you this guy is positive. Any large N conformal Regge theories, especially true for string theory. Yeah, I hope it answered your question why this is negative. Is this clear?
Yeah.
Okay. Yeah. Or another way of saying it, there is a more the argument. Yeah. The MSS way of proving that this is negative is by it's not obvious that it's related to bootstrap, but actually the idea this sign bound is just saying that in the cross ratio plane you can find a contour where everything is analytic, and you can relate this disk in this channel to something that has a manifestly positive sign by looking at the other channel, basically by the Cauchy-Schwarz identity.
Mm-hmm.
So you can also see it from the bootstrap point of view, just by crossing actually. Yeah. So yeah. Okay. And so it is true for string theory. But I want to tell you first one more thing, which is this is not actually trivial. It's highly non-trivial, which is related to a previous comment in flat space. Conformal Regge theory, as I already told you, it satisfies this bound. But if you only consider a single higher spin field, you can calculate the disk. Yeah, you exchange a single higher spin particle. You calculate this continuity. You will see that this continuity itself has the correct sign, but the prefactor here will have the wrong sign, because now for any higher spin particle, J is greater than 2. So if you plug in numbers, you will see this guy actually is positive instead of being negative. So it will be positive, negative. So the final answer is negative, not positive. So for any higher spin particle, any single higher spin particle, it is not true. Or more generally, if your theory has a higher spin, it has a truncated higher spin spectrum, the bound will be violated. It is only true if you have an infinite family of them, and when you do the resum, they magically they conspire together to give you the correct sign. So I think that's very interesting. It somehow is suggesting that this bound is telling you something really how to get a self-consistent theory that UV completes gravity, but that's just speculation. Yes, okay. And if you take the flat space version of what I'm just telling you here, you exactly reproduce our previous observation in asymptotically flat space. Is this clear, actually? What was a question here for this?
Any question?
No, it was good.
Yeah,
it was good.
Okay. Oh, okay. So yeah, as I don't have time, I just briefly mentioned this. The previous two cases look very different, but you can actually interpolate the two. It's very interesting. The way you interpolate the two is what we call the velocity-dependent Regge limit. It's not studied a lot, but I think it has some truth in it, because it, of course, first they interpolate the two, and also there's a reason for that. I think when we study the previous quantum chaos case, quantum chaos usually people study in quantum mechanics, so you fix X and look at T. But really, in local quantum field theory, the chaos spread on race instead of fixed position. So it's very natural actually consider instead X equal to VT. You put a velocity here, it tells you which ray you look at, and then take this T goes to infinity limit. When you do that, you will see that actually this integral still has a saddle. It always has a saddle, but by passing through the saddle, you have to shift your contour. But when you shift the contour, because this alpha of nu have some poles on the imaginary axis, it will have to cross those poles. So the idea is that when V is very small, you always dominated by the saddle. That's the regime where string theory is important. When you go larger and larger in V, you will first wrap the graviton pole. In that case, the graviton will be, the stress center will be killed, but you can still show that the sublinear contribution has the correct sign. When you further increase this V, it will, the next pole it will cross is the first double trace operator. And first double trace operator is just the limit of our previous ANEC result. So once you're in that regime, it is true. We have shown that it's true because of consideration and gravity. So by tuning the V, you can actually interpolate the two regimes, which I find very interesting. And the interesting thing is whatever V you choose, this bound is always true. Yeah, it's so I have my comments. First of all, in this case, which is the conformal Regge theory case, we actually don't know the physical meaning of this positive operator. It's not an energy operator because you can actually write down the energy in string theory, just sum over all the energies of higher spin particles. It's not this. So that's why we finally decided to call this a focusing bound, because it seems to be more related to something telling you that string theory focuses. And you actually see, especially in this velocity dependent case, I calculated and tell you everything's positive by very magical like conspiracy between these coefficients. But everything here is in the direct channel. To really say we get a proof, well, you can say it's a proof. I think it's fair to call it a proof because I assume something for the Regge trajectory. Also, the sign bound on chaos is kind of coming from the dual channel, but it's still not very directly, immediately obvious to us how you can see it, see everything from the dual channel. For example, there is recently a very popular subject called dispersive sum rule, which tells you essentially if you study something in the direct channel, you act derivative on it. Then in the dual channel, you act derivative also on it. But in the dual channel, the derivative will produce you a lot of positive terms. That's why the left-hand side must be positive. And our result certainly is not that, because we tried that. We tried their functionals, but none of them is equivalent to ours. So ours seems to be another one, and it's not clear how they're related now. Yeah, if you try any of them, the right-hand side is simply not sum over a lot of positive terms. There is something magical happening for our functional, at least using their methods, it's not obvious to us. And if I turn the logic around, actually, I can ask another question. People study those positivity conditions using these sum rules, but the physical meaning actually is not very obvious to us. Basically, you look into the space of functionals, you use bootstrap techniques, you construct positive ones, but none of them, like the one I'm giving you here, have a very clear bulk interpretation. So we are hoping that maybe some of them, the conditions there can also be given like a bulk interpretation or something like that. So that would be helpful if we really want to find out more like conditions like ours. It definitely requires more explanation, exploration in these directions. Okay, I'm running out of time. Let me just make a quick summary. So I hope I convinced you that the average bulk ANEC in ADS means this operator equation inequality for the dual CFT, which is the Regge OPE of this quantity is a positive operator. That's what the bulk ANEC is translated. In theories like with gravity. And to generalize this to string theory, we first rewrite this as constraints on correlation functions. Then for that, studying that, you see they're true, and we call them the focusing bound. For example, the one on 4-point function look like this. And well, they are true here by direct calculation and the bound on quantum chaos. Some chaos reason, and they're just true, and we don't know a better reason for it. And finally, I turn the logic here, order here around. When you take the flat space limit of what I just told you, you will get these bounds. And when you study them themselves, they are interesting because they reproduce all the constraints in the CAMS paper coming from causality argument. Okay, as I'm running out of time, I will be super quick here. The first two things I already mentioned. The next thing is here I'm telling you something about the average non-energy condition. Recently, people noticed that actually energy is highly related to the entanglement entropy. There is even proof. There is a more to get that involved, you have to consider more local energy condition, not integrated on the whole null line, but a little bit part of it, or maybe even just a single point. That's called the quantum non-energy condition. It relates the energy to entanglement. And it's very natural to ask, can we actually generalize what we did to understand something like relating entropy and energy and what it means for CFT, for example? That's also very interesting. That's the question about bulk-QNEC. Secondly, we understand this leading order in large N. It's very interesting to extend it to higher order if it's true and what it means. Next, we see that especially in the string theory case, the positivity is coming from really studying chaos or operator growth. So more specifically in ADS2, the bulk N is related to the positivity of something that people call size operator. And I think there is very deep connection there, but we hope to come to that later. And finally, I think I don't have to repeat this here, but I think Regge limit is very important, and the bulk meaning of it is not explored a lot. So I think we can explore more bulk physics coming from the bulk boundary Regge limit. So thank you. That's everything I want to tell you.
Okay, let's thank Yikun. Now we have time for questions. Do you have questions? Maybe at home also. Okay.
Can you hear me?
Yeah.
What kind of limits have you taken in bulk physics? Like you said, also the linearized approximation in GR. Is that correct?
Yeah.
And what does it mean in the boundary?
It means that I'm only considering the leading 1 over n squared term in my 4-point function.
But that's just small g Newton, right? What?
Yeah.
Beyond that, you're saying linearized gravity. Like you
Oh.
don't.
Yeah, that is the same statement as saying I'm considering leading order in G 1 over G, like sorry, the G Newton 1 over n squared or G Newton expansion. Because when you include more gravitons, for example, you consider correct term, it will come with 1 over n to the power 4. Right, because a vertex will give you extra vertex, say a loop will give you extra G Newton.
I see, but in the Rajchandra equation that you showed, you ignored the other terms, right? The second and third terms, and that is related to linearization.
Where? Do you have something?
Much before this, I think. That was in the flat space discussion.
Can you actually repeat your question? I don't totally get it.
Can you go a couple of slides back?
Yeah, sure.
Yeah, this one. Here you ignored the shear tensor and the last term.
Oh, I see.
Linearization.
Yeah, good. In CFT, are you asking about the physical meaning of these terms?
Yeah, I'm asking what approximation is this in CFT?
Yeah, it's probably not clear, but it is the approximation that I'm only considering the leading 1 over n squared contribution to the 4-point function, because each term will come with extra G Newton in it.
I see. So you take large n, large lambda, and also some large back parameter to avoid black holes.
Yeah, correct.
Okay, thanks.
Yeah, no problem.
Other questions?
Thanks for the nice talk. And so here you have related this focusing bound, the Regge OP of two scalar operators, right?
Yeah.
So what will it correspond to the Regge limit if you add spin to the external operators that you are considering? What would that correspond to?
You mean string theory?
No, external operator.
Yeah, external operators.
Sorry, can I say it again? External operators.
Yes.
Yeah.
The question is, how is it? Oh, what external operator I need to take is that the question?
No. Here you have considered the Regge OP of two external operators, and you're related to these focusing bounds, right?
Yes.
Okay. So if you now consider the Regge OP of two operators, but some of them have spin. Do you know the generalization of this on the right hand side? How do you make to generalize focusing bonds?
Yeah, good question.
And would it be useful, or that's also.
Yeah. Let me tell you two things I can think of. First of all, let's just take this 4-point function as an example. Suppose psi is scalar, O is with spin. Then you can also ask if O has if O is the one, if I do OPE for these O's with spins, psi's are without the spins. For that case, you don't get new bounds because like which one you call pro, which one you call tau, you can extend it to, and the boost is kind of symmetric between the two operators. So for that case, you don't get new things. And actually, I didn't say it here. Indeed, for spinning particles, for spinning external particles, if it's spinning and scalar, those bounds tell you something constraining, like the spinning particles. That's one thing. On the other hand, if I really do the OPE for these, if the size are with spins, then the difficulty is this. Psi will not be simply H. You will also get some derivatives coming from the tensor structures. So in that case, it's not clear how C acting on the whole guy will be related to something like energy. Yeah, so it's a good question. Maybe it will tell you something about derivative of energy. I don't know, but it is an interesting question, but we didn't explore that much about it.
Okay, thanks.
Yeah.
Have you checked that this gives you exactly the same bound? Like they have a proof of the same bound using this Regge argument and considering only the stress tensor, and then saying that all the other terms are suppressed by large n, and they get the same bound. Do you get the same, or because this is more powerful, do you get even better? Have you checked this?
Which paper you have in mind? Like, I didn't hear clearly.
I think it's called Einstein gravity from conformal Regge theory or something like this. It's from Nima and others. They use they compute basically TOOT. So it's basically your case, two spinning ones and two scalar ones, and they use the Regge theory. They compute, they take derivatives of Regge theory, that conformal Regge theory paper, they take derivatives, they get the behavior of this TOOT, and they study this and they say, okay, let's only consider stress tensor exchange, such that this is the only thing that matters. And they get bounds on the TTT. And they say all the others are suppressed by n, so we get a bound on TTT, OP coefficient. And they prove the stems bound using this.
That sounds very interesting. Yeah. Maybe you can send me the reference. I don't know.
Okay, I will send you.
It's not obvious to me how they're related. Yeah. Let me say one thing. If we only consider gravity, then our bound is equivalent to the Kemp's bound. So I'm not sure if their bound is stronger or equivalent? If it's equivalent, then it's
I
highly
think
possible
it's
that.
exactly equivalent because the proof also uses the bound on chaos that you use later.
I see. Interesting. I see. Yeah, I would definitely take a look and we
It's
can talk.
probably you'll get the same bound if you do with your method, you do the computation, you get the same bound. But because you are saying that this focusing bound is stronger than causality, and you're only using, okay, maybe it only implies bound on chaos. Okay, maybe it's exactly the same. Yeah.
I see. Yeah,
Maybe-
sounds very interesting. I didn't know that paper. Maybe you can send it to me.
Yeah, I will send you.
About it. Yeah, thank you.
Any other questions?
You also mentioned that you only apply this to 4-point functions, but you could be applied to higher point functions.
Yeah. Any two point functions.
Yeah, what could you gain by applying to higher point functions?
I don't know, like let's see. I would say let's see how to say this. Ideally, if there is some very high point function that you don't know the answer, it probably can give you some bound on how that can be. But if you already know the answer, I think it must be true. That's I can tell you. Like, yeah, right. So, yeah, I don't know. If there is a correlator that's not known, there's some unknown coefficient, I think we can probably bound something. But if it's already known, if it's just hard to calculate, I think if you do hard enough, it must just be true.
Thanks.
Yeah.
Okay.
Is there any question at all? Can you see?
Let's see if there's any question at home. I don't think so. Any other questions here? Okay, so let's thank Yikun once again. And we can stop here. Thank you.
Yeah, no problem. Thank you.